All right, welcome back. So today we'll be talking about imaging by lenses and then some applications of the theory in our vision and some optical instrument. Okay, so let's dive in. Um, so last time we talked about image formed by curved mirrors. Now that's based on law of reflection. Now for law of refraction, Snell's law, you can also actually take a look here. So if you have an object in front of a transparent material, so where the light ray comes out from the object here, so we'll just use a single point. Or if you look at the figure down here, this arrow as the object here, from the top of the object here, you can draw two rays out of that P just arbitrarily. But we kind of intentional do this, so we pick like a line that is parallel to the central exit here, and then apply Snell's law one time there, and then we do a second one. This one will actually pointing towards the center of curvature of this curved median here. So then this is coming at the instance angle. It should be not deflected. Okay, so the refractive rays, okay, they actually intercept in the media. So here, so then you actually have a image here. Now the two refracted ray, they do intercept, so this is going to be a real image. That means you can capture the image on a screen. Okay. Similarly on here, so if you have an object P here, you draw two rays out of that again, then apply Snell's law on the two locations where the rays hit, and then those two will intercept at some point P prime here, or in some scenario, you might not have them intercept. But if that's the case, you can back extend the refracted rays, then they appear to be coming at a point. Okay, so then image in this case then would be virtual. Okay, so you can see if you have object in front of surface, a transparent material, then you actually be able to form either virtual or real image. Okay. All right. Now we'll focus on just thin lenses. So that means the lens part is small, and then for the so that in that case you actually have several different types of lenses. Okay, so convergent lenses, two main category: convergent and divergent lenses. Okay, and then under each of these two convergent and divergent lenses, you actually have other different types of those lenses. Okay, so convex meniscus, that means they are both curved towards one side. Okay, and for plano convex, that means one side is actually flat and then one side is curved. So it's curved outward, so it's called convex. Okay, and then double convex would be both sides will be curved outward in that case. Concave meniscus will be curved in here. Okay, and then also this side will be curved as well. Plano concave, so again, one side curved in, the other side flat. Double concave, both sides curved inward. Okay, and focus for this class will be on just double convex and double concave lenses. Okay, all right. So we'll take a look at the double convex lenses first. Okay, and then we'll just say convex lenses. Okay, so in that case, so it's by default it's referring to concave or double convex lenses. Okay, in that case, so light ray hits one side of the lens, and they will get refracted twice. Okay, and in that case, for convex lenses, they actually, if you have parallel rays comes in, they will actually be intercept at or they actually will, the refracted rays will meet on the other side of lens at the focal length. Okay, and this is similar to if you have two prisms like these two. So you can look at the rays. Okay, so kind of the rays will be originally they are parallel to each other, and then afterward they kind of converge. Okay, so in that sense. All right, but for the lenses, all the rays, parallel rays, get refracted, and then they will be meeting or intercepting the common point called focal point. All right. For concave lenses, it's the other way around. So it actually divergent rays. Okay. So if you have parallel rays comes in from one side, and then the refracted ray will be diverging on the other side. But if you back extend those rays on the other side, so they will actually appear to be coming from this same point, which is the focal point. Okay. That concave lens. And the way this works is similar to if you have two prisms again, but you put them upside down. So then the parallel ray comes in when they deflect out, they are actually diverging from each other, okay, as they exit. Okay. Again, this is similar to the curved mirror. So we'll have three principal rays for lenses. P ray, again, is parallel to the central exit, and F ray is the ray drawn towards or through the focal point, depending on if you have concave or convex lenses. For concave, then it's drawn towards the focal point. For convex, it's drawn through. Okay. And then there's a middle point ray, which in the mirror's case is the center ray, center of curvature ray, C ray. But in this case, we call it mid ray, M ray, midpoint ray. It goes through the middle of the lens, and then if the lens is thin enough, then it will not be deflected. Okay. And then this is an approximation because this is a thin lens, so they will probably be deflected slightly, but because the lens is thin, so then we can kind of ignore that small diffraction there. Okay. All right. So use those three principal rays, we can trace the image just similarly as we did for the mirror. So three rays, again, P ray parallel to this principal exit will be deflected going through the focal point. Midpoint ray will just go right through, and focal ray, F ray, drawn through the focal point, deflect parallel to the exit for convex lens. For concave lens here, again, P ray deflected, so appears to be coming drawn from the focal point. Okay, the F ray drawn towards the focal point will be deflected parallel. Okay, and then the mid ray will, again will just go through. Okay, so in this case, it's diverging the rays as they exit. So then if you back extend, then they should be intersecting at the same point over here. So back extend, this green one should come here. Okay, so this then will be the location of image, and it will be virtual image. For the convex lenses, okay, depending on where you place your object, okay, so you could get the real image, okay, or if you get very close to the lens, then you'll be just getting the virtual image, okay. All right, so let's move on here. So again, so this is kind of just repeating what we saw on the previous page on the right-hand side of the image. So I can go quickly here. So kind of similar to this guy, okay? All right, so you can use the three rays and then to find the image. So in this case, you locate your image, this will be virtual, okay? Virtual image, because you have to back extend those rays exit of the lens to meet here. So that's your virtual image, okay? For convex lenses, so it depends on where you put your object, okay? So if your object to lens distance is greater than the focal length, then you're gonna to get a real image upside down, okay? So for real image is also inverted, always inverted, okay? And if you are placing your object within the focal length, so DO is less than the focal length, then you are going to get a virtual image, okay? So the rays come out, then will become diverging in that case. So then you get a virtual image, it's upright virtual image in that case, okay? All right. So again, a few um, kind of summarize for these two lenses. So F positive referring to convex lenses. Okay. So then depends on your object to lens distance. If you are greater than the focal length, you get real image. DI will be positive, and the magnification will be negative. Okay. If you are placing your object within the focal length, you'll get virtual image, and the DI then will be negative. Okay, because of virtual image. And then the magnification will be greater than 1. For the concave lens, so F will be negative, image will be always virtual, DI will be negative, and then magnification will be less than 1. Okay, for that. You can derive the thin lens equation, again, similar to what we did for the mirror equation. So it's pretty much the same. You use two sets of similar triangles, and then you set up those two equations of, for the case of here, it will be HI over HO equals F or F or DI minus F here over F, okay? And then for the second equation, HI over HO will be equal to DI over DO, okay? And then just derive through for the few steps, you'll then arrive at this thin lens equation. So turns out to be the same as the mirror equation, okay? And magnification is defined as the same way is the size of your image over the size of the object, okay? So if it's real image, HI will be negative, okay? And then this is equal to minus of DI over DO. All right. On sign conventions, so focal length is positive for convex lenses because convex lenses can converge rays, okay? And it can also diverge if you place the object close to the lens within the focal length, okay? The focal length is negative for diverging concave lenses. And magnification is positive for upright image. It's negative for inverted image, which means real image then it's negative. Image distance is positive for real image. If it's virtual image, you get negative on that. Okay, object distance is positive for real object, and then it's negative for virtual object. So this is referring to if you are using multiple lenses at the same time. So then sometimes the virtual image could be the object of a second lens. Okay. All right. So one example here, it says an object with a height of 2.54 centimeter is placed 36.3 millimeter to the left of a lens with a focal length of 35.0 millimeter. So it's positive 35.0 millimeter. That means this is a converging lens. Okay. Convex lenses. Where is the image located? It's asking what's the height of the image. Okay. So again, based on the two equations, the lens equation is exactly the same as the mirror equation, and then the magnification equation, okay, for the second equation there. All right. So this is HO, the object height, and this is the DO, object distance to the lens, okay? And this is F, focal length, okay? And then we are looking for where the image is located. So that means we are looking for DI. So 1 over DO plus 1 over DI equals 1 over F, okay? So we are having DO and F, we can solve for DI. So DI, 1 over DI will be equal to 1 over F minus 1 over DO, okay? So then DI is 1 over F over 1 over DO and to the power of minus 1. And we just plug in numbers there for 35 here, and then 1 over 36.3, okay? And then get the inverse of that. So this will give us a rather big number, they are in millimeters for the numbers, so 977, okay, on that. So B is asking you what's the height of the image. So you're looking for HI, okay. Now, and the second equation for the magnification, that's HI over HO, and it can also be written as minus of DI over DO, okay. So we can focus on the second part here because we now have DI and DO, so then we can calculate the right-hand side of this part here, and then HO is given, so we can figure out HI, okay, so with that. So in HI then will be equal to minus DI over DO and times HO, okay, so minus 977 millimeters over DO is 36.3 millimeters, and HO is actually given in centimeter, so that's fine because the millimeter and millimeter cancels, okay? So we can still keep that 2.54 centimeter, okay? That's in centimeter. It's a little bit messy there. Let me see. Maybe I should just start a new line. Okay. All right. So minus 977 millimeter over 36.3 millimeter times 2.54 centimeter. Okay. So millimeter cancels. The answer, final answer will be just in centimeter. Okay. So this gives us minus 68.4, which is in centimeter. Okay. And the negative sign, that means it's actually inverted image, which is a real image. Okay. Okay. So, and maybe on this one, you can practice your ray diagram as well. So we can probably draw this. Okay. So this guy, that's a lens. Okay. And 35, 35. Okay. So 35 millimeter on one side and then 35 millimeter on the other side. That's the focal point, And you have an object which is just located a little bit beyond your focal point. Okay. This is 36.3. Okay. So you can have a P ray that will come out through this guy. Okay. Focal point on the other side. And then you can draw a center of ray. So going down here. All right. So somewhere there. And so your image will be somewhere down here. Okay. So for some reason I couldn't draw accurately with this pencil on this iPad, but you can draw on your figure will be more accurate. So you'll find that the image is very far away if this is properly according to scale. Okay, so it gives you very large DI, okay, in A, and then also image will be larger than the your original object. Okay, all right. So going back to the slide. All right. So then we'll turn to chapter 26, which is about the how our eyeball works. Okay, in that case, and then correction of um, your eyesight if your eyesight is not the perfect one. Okay, so um, for this is how it works. So this is kind of a convex lens um, in your eyeball. Okay, and the ray comes in will be converged. Okay, so if you are nearsighted, then this is what you have. So the image then is not formed on the retina. Okay, so to correct that, you need to wear divergent lenses. Okay, so in that case, diverge those rays, and then now you can correct, so the image will be on the retina over there. Okay, and for the far-sighted eye, it will be the other way around. So image will be formed behind the retina, and you'll need to wear convergent lenses. Okay, this typically happens when people gets old. Okay, so then they need those lenses. Okay, now objects from far away actually will appear smaller. Then if the object is near the eyeball, okay, so but the object size in these two cases is the same. Okay, so just depending on how far away the object is. Okay, so you can see from the ray diagram here. So in this case, the image is smaller, and then in this case, the image is bigger. Okay, so they just appear to be larger when they are closer. Okay. All right, and then this is a schematic drawing for compound microscope. So it's basically using two lenses. So one is called objective lenses, which is placed before the object, and then the other one is called eyepiece, placed in front of the eye. So that's why it's called eyepiece. Okay, so the object in front here will form a real image behind this guy over here. So this is magnified. So typically you place the object out beyond the away from the focal length to the lenses, okay, or further distance to the lenses than the focal length. And then you get enlarged image over there, and then use a second piece, you can enlarge that image again, okay, to be viewed. All right, so that will be it for today. We mainly talk about just imaging by lenses, and then briefly on the application of the vision and optical instrument. Okay, so we'll stop here and then come back next time. Bye.